Welcome to my new calculus channel. My name is John Gabriel. And in this lecture, which is the last lecture of this series, lecture 13, I'll be discussing the Gabriel Polynomial. And of course, there are many, many more features of the new calculus besides just what you've seen already and what I've shown you and what I'm about to show you in this video. I would encourage you to study my free ebook and to research these things on your own. So without further ado, let's begin. Now, we covered in the previous chapter the definition of the integral, and the one prior to that, the definition of the derivative. So just very quickly, what led to the ideas, or what were the ideas that led to the Gabriel polynomial? Now, the majority of you will no doubt have not seen any of these things before, because you do not see them in an undergraduate course in mathematics. So if you obtain a BSc, chances are you haven't actually looked at this theory, which is based on Newton's finite differences and his interpolation polynomial. It's the kind of material you'll normally come across in a postgraduate course. So I sincerely doubt that the majority of you have even come across his interpolation polynomial. And perhaps after you have watched this video, you might go off and spend some time studying Newton's theory on finite differences and his interpolation polynomial, and then come back again and read what I have to say, because then it will make a lot more sense. So Newton worked a lot with divided differences, and in his very last in the very last part of his De Analysi, his famous De Analysi document, he has a proposition 4 here, which is the theory of his finite differences. And in this proposition, he constructs a little diagram here on the side, which is a little deceptive because it's actually a graph, and it makes more sense if you rotate the diagram this like I've done here, so that you can get a better idea of what it says. And so all he does is he takes fixed x coordinates, equal lengths, and then he takes the midpoints, and he calculates finite differences using these ordinates and this distance here. So if you study how we got calculus, I discussed that in that document. I'll also put a link once again in the details section to this document, so you can study that if you want to and see what his interpolation polynomial looks like. So although there is nothing wrong with Newton's approach, what Newton has done there is really approximation and more approximation. Newton was the master of approximations. And of course, none of Newton's results were closed form. That means you'd have to basically find an approximation every time you use his interpolation polynomial. And then of course later Taylor and Maclaurin found their series using the interpolation polynomial. And all that is discussed in my book on how we got calculus, so you can read it up there. And of course, they didn't really make such a quantum leap, because most of what they wrote down was, in fact, information that Newton already knew. And I define the finite differences in terms of the arithmetic mean of each interval. So I use a notation mu, and mu superscript 1 and sub 0 means the first order mean and the first difference. So mu always refers to the abscissa of the mean, and this following diagram explains. And this here more or less is the analog of what you see here in Newton's De Analysi. And I first studied this in my teens, okay? And I later came up with this scheme. Now, my first divided differences are the same as Newton's, and there's essentially no difference between his first order differences and mine. And so, for example, x sub 0 and x sub 1 is equal to this, and it's equal to this in my new calculus, and also this in my new calculus. That's x sub 1, x sub 2 divided finite difference. Now, Newton's second order divided difference is where I branch. And basically, Newton didn't really use the mean any longer in his second order difference. So he simply just formed the difference as you see it there and didn't worry whether or not the abscissa that he used was the arithmetic mean. And you can compare that with my definition as you see here. So my definition changes, and this is what you have. And of course, you can work from this particular equation here to get to this point here, okay, by simply multiplying this throughout by this denominator here. And then again, you can simplify further by leaving that alone and expanding this into this divided difference. And then again, rearranging the terms by taking that over to this side and then leaving that on the side that it's in. And then, of course, simplifying it so that you eventually just have f of x sub 0 on one side by its own, and the entire closed form as you see it there. Now, don't worry, I'll show you an example with this in a moment. But before I do, I want to tell you that this isn't the only closed form. You can have closed forms up to the nth derivative, okay? So if the function that you're dealing with has more derivatives, you could have this form or another form. And I'll show you in a minute another form that you can get from this. But let's see an example. So if we look at this particular curve here, x4 plus x cubed minus x squared plus x, then we wish to estimate f of 3, that's x sub 0 is equal to 3. And we can see that we can simply go ahead and substitute those inside, and we can find the values for the mu's, okay? And we can do that using an iterative method, although in reality, we don't need to do any of that, as you'll see in a while. But I'm just showing you that the method will work, and it will give exact answers. So using the Gabriel polynomial, you will arrive at 102, which is exactly the correct answer. If you look, however, at the approximation using the Taylor series, it's never exact. It's 102 point some fractional value, which you find after. So it's not surprising that Taylor series always results in approximations, because it's not a complete closed form. It's always what you call in the mainstream an infinite series. It's not really infinite. It's really a partial sum followed by an ellipsis, as you've seen in the previous chapters. So if you compare my equality with Taylor's approximation, that's what you have, okay? And now, whilst the Gabriel polynomial is not really designed just for the purposes of approximation, it actually outperforms the Taylor series for any function, okay? And I've given you an example here with this particular function here, in fact, the one that I used in the document. And I show you that as these are the means, these abscesses here in the pink are the means, and these are the coordinates that you see in the document, okay? These x0 and x1. And not to spend too much time, if you decrease the space of your intervals, you will see that the Gabriel approximation is always better, and the error in this particular case is less, so that when you get pretty close, even like so, let's just see here, oops, okay, look at that. So even with 0.01 as a difference, already the Gabriel polynomial has a correct value, and the Taylor approximation is still not the exact value. Obviously, if we move the green point on the zero, if we move the green point over the abscissa that we're trying to approximate the y value, then they'll be exactly the same, okay? So you can watch the calculations. I'll also put a link to this applet so you can download it, and you can see the calculations in real time, see what's happening. And there are many advantages of the Gabriel polynomial. You can have a fixed number of terms variable up to the nth derivative. It always provides far better approximation than Taylor's for all functions using estimated mu's. And remember, that was not really the purpose for it. It's excellent in causal systems where the function is assumed to be continuous and smooth, but there is no mathematical model known. So for example, if you look at this particular format here, this closed form, these values here might be coming in from some kind of mechanical or electronic or analog device. They don't necessarily have to be based on a mathematical model, but on the assumption that there is a continuous and smooth model that works for that particular system. So it's also excellent for curve fitting and non-linear regression, and many other things which are too much to discuss in this video. And of course, a variable number of polynomials. So now in this example here, I've only shown you the first one here. In other words, up to the second derivative. But since this here does have 3 derivatives, the next format would be the one that you see in the bottom line here. So all that you do is you would change the last subscript from 0 to 1, and then put in the next derivative with 0, 3, where 3 is the order of the derivative, okay? And that would give you the closed form for the third derivative. And all of these closed forms always provide exact values. Well, they're exact in the sense that you don't have to approximate as you do in the Taylor series or Maclaurin or any other approximation method. So the Gabriel polynomial is quite fascinating, and I've also given you another example here with the normal distribution, where you can move these points and you can see what happens as you move x1 closer to x, where the Gabriel polynomial is more accurate and very close. You already have the correct value of the Gabriel polynomial, even though the difference is 0.40 followed by 3. Okay, so the error here is approximately a difference of 2 between the two polynomials. So that is the Gabriel polynomial in a nutshell. Of course, at a very far distance, it doesn't really matter, because all we care about is when the points are close together and we have an equal number of derivatives with the mu's in the intervals of those derivatives. And then, of course, if you have second order derivatives, then you'd be looking at the differences between those two mu's, obtaining new mu's, which are arithmetic means. So I think I've said a lot in this video, and unless you have been studying mathematics for a very long time, you'll probably be a little overwhelmed. But don't be overwhelmed, because you can actually become very competent in this material quickly if you study the material, the information and the articles that I've given you. And of course, you can discover many other things that I haven't shared with the public, simply because this on its own has been too much for the brightest amongst you. So at any rate, I'm going to just save these and close them, and I'll provide links to these applets that I've used here, and you can take a look at them. But I said I was going to show you how to go from this form to the next form. So let me do that very quickly. So we just pull up a blank paintbrush over here, and let's start quickly. So where are we? Let's see, where's my cursor? Let's see, oops, nope, I didn't mean to do that. I want to use a pen and I want to write. So we know that the third order difference will be x0, x sub 1, x sub 2, x sub 3, and that's going to equal to the difference of the second order differences, which you see here, right? 1, 2, 3, like so, all over mu 0 to mu 2, 1, and that's going to give you the second derivative with mu 0, 2 minus f2 mu 1, 2 all over the denominator, which stays the same, right? And that, of course, this here, of course, is the same as this, okay, 3, which is equal to this expression here, but we can expand it by multiplying by the denominator, so we can basically get m 0, 2 minus m 1, 2 on this side multiplied by this, and on this side here we can continue to manipulate this expression here, and I'll explain to you in a moment what's going on. Just a moment. Let me write this down so that I don't make any mistake with the subscripts and the superscripts. So you have that, and you have this here. Okay, now this part here that you see, this part here is actually this, okay? And this was just left alone down here, and of course we had multiplied by this factor, so it went over to this side. All right, so then if we continue with the simplification, what we'll end up with by degenerating this again is this expression here, f m01 is equal to f prime 1, 1 plus 0, 1 minus, oops, I didn't mean to do that, that's mu there. Hang on a second. Just delete that quickly. It's actually that f2 mu 2, 1 plus mu 0, 1 mu 1, 1 mu 2, 0 mu 2, 1 f3 mu 3, 0. Okay, and then from this, you can finally leave everything alone except this expression here, this one here, which is actually equal to, this is equal to f of x 0 minus f of x 1 over x0 minus x1. And now finally, if you do that and you isolate f of x, you'll end up with the form as follows, the closed form as follows. Plus x0 minus x1 prime 1 m1 plus, again, x0 minus x1. All right, I'm trying to write as fast as I can. 2 like so. And then finally, this last term, which is which is that. Okay, to 0 minus m to 1, f of 3, like so. Okay, so this is basically how you get back to the term that I showed you in the applet. Okay, so the term I showed you in the applet, this becomes a 1, and we add this last term here. Okay, and of course you want to get the fourth difference, then you'd change this particular 0 to a 1. The next one would be f4 m4 0, and it would have all these factors plus the next one, which will be, I'm sorry, this is a 2 here, not a 3. The next one, which will be a third order difference factor, and so on, depending on how many places you want to expand your polynomial to. So that's pretty much it for this chapter. I think I've shown you a lot more than the majority of you are going to be able to digest. And I've also given you an explanation of the approximation method in these last few pages, showing you how Newton actually finds it and how to write it as an equality, and an example there with it again. And finally, in the last section, I have final remarks to make. And this ebook, which I gift to you, and of course I have revealed nothing new apart from that which I've already shared in previous articles or videos. There is more knowledge than I can share with you in one particular video. So I have given permission to Brandon Narr to edit and publish his ebook if he so wishes, but nobody else may change the contents. You may download it, print it, make copies, even translate it into your own language. I don't mind. And you can even sell it once you've translated it, but you may not change any of the contents, okay? So I'm even allowing you to make money off it. Now, you all have Brandon Narr to thank, because he inspired me to write it, and I really didn't feel up to it. In fact, I wasn't motivated until Brandon encouraged me to do this. So, and remember, this ebook is not really a very large book. It's only about 123 pages. I didn't really put examples of all the different kinds of, differentiation problems, which are, in my opinion, trivial, and any old fool can do it once he knows, how the definition works. And that's pretty much it. So I hope you've enjoyed this series, and that you'll study the new calculus, and that you'll learn how to use the well-formed concepts that I've revealed to you. This is a new calculus channel. I'm the great John Gabriel. Till next time, goodbye.